So yeah, hello guys, and for this video, will continue from what you call electrical potential energy. But because I think in the last class we already did the exercise 6 and the solution for that. So now we'll continue with electrical potential energy, and let's start now. So as you can see from looking at it, or you can say from looking at the electrical potential energy, and I think so you're not new to this term. You know, it's about energy stored in an object. So in simplest term, you can um, understand this. Let's say you have a battery that has a potential energy which is stored in it, more or less in simplest term. And when you measure the value or the voltage across the battery, that is your electrical potential, or we in this case we call it a scalar. So yeah, no, so for now from then now we are going to, that's your electrical potential energy. Then now we are going to try to um, understand and see how can we use our voltage or electrical potential value to obtain our electric field, or E, the value for E, because in the previous examples we used Coulomb's law and Gauss's law. So now in this case we'll use electric potential to figure out how we are going to calculate E. So yeah, you can read through this. Then here we have our some formulas they give us. This formula, just remember, is for work done now. So yeah, it's in terms of, it's a derivative, but and later on as you will see it here. But for now, where they say you have a point charge Q from point A to point B in an electric field. So let's say you have a point charge. Let me draw it here. That's your A and that's your B. Then somewhere around, let's say you have a point charge, or that's your Q. So we want to see with this equation of potential using that, or that what is the work done by B and A, or what is the work done on point Q, if you understand, using our these functions here. So that's what we are more or less going to do. So from Coulomb's law, the force on Q is, I think so you do know the force equation, where F equals Q times E, our electric field. If you remember, our electric field equals force divided by Q. So that's where we get that. And the work done, I think so you do, I remember, it's just the energy, or energy displacement on a point. So in this case, we are going to um, calculate work done, or energy that was invested, or was applied on the point charge Q. So that's more or less the equation, and the dl is just the length, which is just means when they say dl, it's just the smallest length, or very small. So just remember that. And then also they say negative side indicates the work done. So it just indicates that uh, uh, we are losing energy. So this negative sign just indicates we are losing energy in the simplest term. And then this equation we also use to calculate total energy. So yeah, that's the formula for that, which is we use our electric field and our length between A and B to calculate our work done. And then in the again talk about the potential difference between A and B. So we find our work done formula, and then to find your voltage across those 2 points. So let's say with this formula, uh, you'll find your, and that was B. I'll say this is A. You will find E times DL. So this is using this, you will find your work done. Then if you just send Q this side, or you divide everything by 1 over Q, and even this side 1, it is 1 over Q, then you will find the voltage across the system. So that's what they only say, or a voltage between the 2 points, your A and B. So the voltage here, that's more or less that. And then you can also read through this what is to note and how to determine your values at A and B. But then let's continue. And as you can see here, potential, we can potential energy calculated, you can say voltage calculated using Coulomb's law, where we have Q divided by 4 pi epsilon naught, which just remember this one is a constant, and then your R is the distance. So you can say R is the distance, oh yeah, between two, or 2 points, you can say. So just remember that. Oh, in vector, so R can be a vector. It's most of the time we work with three-dimensional objects, as you can see in a form where we have two vectors. Then again, they read the same thing. I think it's the same slide. Yeah. On potential energy. So I hope you do understand the formula usage here. It's much better when we use examples or something like this. So let's say we have example 7 with us, where they ask us to calculate our we have our question 7, where we ask two charge J's, which is minus millicoulomb, minus 4 millicoulomb and 5 millicoulomb, located at these two vector points. Then we need to find the potential uh, at, what do you call, 101. So that's a point. So let's just draw a simple rough diagram. So let's say this is our point 4 millicoulomb, that is our 5 millicoulombs, and we have our point somewhere there, right? So we want to see what is the voltage applied to this point, or we'll call this, let's call it VR, right? So the voltage applied to this point here. So that's the only thing. Then so voltage supplied at this point. So you know our voltage is going to be V or VR plus our voltage from this point to this point. So you can call this, maybe I'll call this V1, this one V2. So we must add V1 plus V2 at that point here. And then they say assuming zero potential at infinity. So just remember at infinity our voltage is 0. So if it's 0, we add another term, you can say it's our initial conditions, which you can say it's V0 most of the time, or C0. V0, which is going to be the same as 0 volts, so we don't have it here. So that's why when they say that, so we leave that part out. That's why our condition is that. So it's at infinity we'll have zero also. They when it reaches some point or too far from, then we almost measure no voltage across it. So that's all they mean. And what do you call? Yeah, trying to explain. Then if it's like this, then I think so we can do few things before we go to the formulas. We can calculate our VR. I'll call this R1 and R2 minus R1. So we need the magnitude of VR minus R1, then we need the magnitude of we call VR2. So these are the two distance we are going to use to calculate our voltage. And the formula we are going to use, I think so you can go back to the notes, or let's see, let's go there. If we go above, this is the formula we are going to use. So it says we have our V equals Q over 4 pi epsilon naught, then our distance between R1 and that's for R1, so I'll call this. Then for V2, you will have again this epsilon naught, then R times R2, or the magnitude, just remember with a straight line. So that will be our values. So I'm just showing you the formula. If you understand the process, then I think so the calculations or putting these values into a calculator is very simple. As you can see, they do show us these values in details. They use this formula, and as you can see, we have here C0, or you can say our potential at 0, or our initial condition, which is also 0, as I said, because of this condition, where our voltage and infinity is 0. Then that becomes 0 also. Then from there, it's I think so it's very simple to calculate your matrix multiplication and everything. So I won't go further on this. I hope you do understand this part. It's just try to understand the diagram, or when you get these type of question, try to draw the diagrams and just put everything there and see what are the information given to you. And from there, see what they want. In this case, I think so they want potential at once. So we say our voltage at these 2 points must add up, right? So yeah, then that will give you this answer there. Now we come to Maxwell's equation 2, or the relationship between B and V. In the simplest term, I can explain the relationship B, or the relationship between your electric field and your potential or your voltage is the simplest is if your you can say your electrical potential or your V will be a lot or high uh, over a short distance, or over a short distance. So let's say as if the distance between your V and R E is almost 0. So we will be high, and your electric field will be strong. So it just means the higher the closer the voltage is to a object or electric field, the stronger your electric field will be. In simplest terms, you can say that. And then if your electric potential changes slowly, or yeah, so just remember, I forgot this thing. Your voltage, the faster it changes over an electric field. So let's say you have this object, right? Then it has some electric field. right? The faster the voltage changes across this electric field, the switching of the voltage is fast. The stronger then your the stronger the electric field will be. So, if fast change in voltage, then your strong, then your electric field will be strong, or your strength of the electric field will increase. That's the second law of, in simplest terms, that's the second law of what you call Maxwell's equation. And then if the potential changes slowly, the electric field will be weak. So if your voltage change is slow, if your voltage change is slow, then your electric field strength or strong strength will be also low. So that's your more or less your what do you call the relationship between electric field and your voltage. You can read through this, but as you can see, this is the equation they give you that goes to zero. So that's the second law of. Then applying Stokes theorem, you can also go check that out if you are interested in what is Stokes theorem. But in this case, we will just focus on the formulas and how they work in an electric field. I hope you understand that. Then you can go also further read through this. That's the gradient of V, but then they are much easier to understand through an example. So we'll calculate an example. So they say E can be found if V scalar is known. So in this case, I think so for the next exercise we'll find our E using our voltage V. So let's start. Let's see what does it say. Given the potential V, I think so. So our voltage is already given here, which is this. Determine or determine the electric field density. So we need to get our D at this point, which is and just remember, as you can see, there is a pi. So this one is a spherical coordinate. So we'll use spherical coordinate. And as you can see, the angle is also in radians. Just remember, we'll always use, just make sure it's either radians or what do you call degrees. But in this case, or wherever you see a pi, it's most likely radians. So it's a spherical coordinate, right? So I think so. We know that. Let's go to this one. I think so. We do remember our electric flux density is epsilon times E. Then our electric field is change in the voltage. Or not this one. It's going to be. Then our electric field is what do you call change in the voltage, or there's just distance triangle. So we need to calculate our electric field, then we calculate our what do you call flux density. So that's what we are going to do next. Now to calculate our electric field, we'll go back to this formula. To calculate our electric field, we need to calculate our change in V. So to calculate change in V, or change in our voltage, our formula needs to be, let's say we have three values here, right? We have R, theta, and phi. So we need to differentiate everything in terms of all of them. R, we need to differentiate V in terms of R. This just means, if you can understand, this small triangle just means we are differentiating our voltage in terms of each of them. So it's a partial differentiation now. So with a unit vector, so we'll have our partial differentiation in this case where we have our change in V over, we'll calculate in terms of R, that will be our, then we have our unit vector in terms of R. Then again, so just remember this symbol just means partial differentiation. Again, we calculate V, then we differentiate it in terms of theta. And our unit vector is theta, A theta, then plus, we again differentiate in terms of, um, we have three values here. So let's say, I think so, if we didn't have cos of phi, we won't differentiate, but then it will be just zero. But I think so we'll still differentiate in terms of cos of phi or cos, or let's say if we didn't have theta, you still differentiate in terms of that. It's not there, so it's just going to be zero. But it's a good idea to differentiate such that your equation is, mm, so such that, or you don't make any mistake. So you can say this is the standard form for changing V. And if we read through that, I think so they did say we get a differential form. Okay, they don't, but then yeah. Then from here you just differentiate V, or you just find it partial differentiation. So for us, in terms of R, it's going to be, I'll do few them. I think so from there it becomes very simple. Sorry about that. So it will be, if we differentiate in terms of R, I believe it's going to be 20 over R cubed, and then these two are just the constants. So it will be just sine theta and cos phi. Then you do the same for d, or change in V over d theta, then change in V over d phi. And yeah, that should be simple enough, so I won't go through that. Then your final, or your differentiation should look like something like this. Or let me just do, for those of you who are confused, you can do it like this. You just differentiate in terms of R, which is 10 over R squared sine theta and cos phi. Then you differentiate this in terms of V. You'll have 20 R cubed. I think so it will be minus 20. Yes, I made a mistake in the previous one. Then the rest will be the same, sine theta and cos phi. So you do the same for your theta and your phi. Mm, So and when you do this, I believe your final answer should be something like this. Or no, not the final answer, because there are some unit vectors also which you have to substitute, but then you can substitute in the value. So your electric field, or E, will look like, will be, uh, it will be final answer, 20 over R cubed Or it's not the final answer. You can more simplify cos theta AR. Now that one is phi. Just remember that. Then our unit vector for AR minus 10 over R cubed. Then we have cos theta cos phi. Then we have our A theta plus 10 over R cubed, which is going to be sine phi. A phi. So that will be your E. So this is where you substitute your E to this equation there. And then you also substitute the other values. So you will have your D at, it was, I think so, 2 half pi and 0. So you substitute these values. So that's your R, that's your theta, and this is your phi. So you substitute these two values in this equation here and you multiply it by, so it's going to be epsilon naught E. And then you substitute these values in your, so at 2 pi over 2 and 0. Then if you substitute them, you should get, or your final answer more or less will be um, well, it's just substitution. Then your final answer should be uh, we can say epsilon times 20 over 8 times our unit vector of A R, which will be will not multiply it out, but then if you multiply it out, it will be AR unit vector picocoulomb per meter squared. We are going to surface area. So that will be our value. I hope you do understand that and this part there. So now they say that's 8.1. So let's do 8.2 here. So for 8.2 they say we need to calculate our work done in a moving or in a moving work done in a moving at 10 microcoulomb charge. So we are going to calculate our work done on a micro 10 microcoulomb charge. So the formula we are going to will be this one here. Okay, then we have our electric field already in terms of our L or length. Alright. Then if you substitute this formula, I believe our basic formula will be and I think so you do also remember our voltage of A B equals what? Work done divided by Q, right? So we know our voltage for A is going to be, we use the voltage formula which is already given. Just remember voltage at any point. So in this case we have 10 over R squared, and this one is very simple, times sine theta cos phi. So our voltage at A will be uh, it's going to be your first you let's just say it's R squared sine theta cos phi. Then you substitute these values where our point A is at 1 comma at 30 degrees and 120 degrees, and as you can see this one is in degrees, so you substitute these values. So this one again is your r, your theta, and your phi. Then you do the same for VB. Understand? I believe so, yeah. Then do the same for VB, and when you get that, then I think then your final voltage or your voltage here, your voltage here will be so if we have work done, then I think so you know your work done will be VA B times Q. So we'll have our Q times A VA B, right? Uh, we'll have our minus Q here. Forgot about the minus. Yeah, that will have our minus Q there. Then therefore formula will be then it will be minus Q. Then we need the voltage difference between A and B. Then it's going to be voltage across VA minus voltage across VB. All right. Then from there, I believe you can do the calculations. Then that's going to be 10 nano coulomb or micro. I mean, this one is micro coulomb. Then your A is given there, and your B will be the same. So your VB at our point B was 4 degree, 490 degrees and 60. So just substitute this one even to in this formula on top there, then you will find your VB. Then you change your, then you will find your work done. And just remember your work done, the unit for it, or the unit is joules, J. I hope you understand this part. So that's our exercise 8. And as you can see, they do the same thing. So this symbol just means it's the partial differentiation in terms of all of them. And as you can see, work done is also simple. Then we also come to work done. So this formula is, these ones are used when we get two different surfaces, or this formula used when we use different surfaces, like here as you can see line charge, surface charge, or what do you call it, volume charge. So it's the sum of different surfaces. That's just remember, but still it's, this one is Q and this one is your voltage. That's that. And let's do our, let's do our number 9 exercise. I think the next one is exercise 9. So at exercise 9 they ask you how, or not, or but then calculate the voltage or work done. No, what do you call on work done on the 3 points that are given to us, which if you say one is at origin, so let's do this. One will be at origin here. that line. So one, this is our origin. So this one will be here. So which is -1 nano coulomb. Then the other one will be number 4 nanocoulomb 0 0. Okay, so we have our z-axis. So I'll call this z, call this x-axis. So in this case, our y-axis are 0. You can see, so I didn't include that. Then at z-axis, we have our one of them there, 4 nanocoulomb. Then at x-axis, we have our values at 3 nanocoulomb, as you can see. And the coordinates are given. So you can say this one is 0, it's 1, 0, 0. This one is just 0, 0, and 0. And this one is, you can take it as 1, it's 0, 0, 1. So the question says find the energy of the system. So we have three system or 3 points here. So I'll just draw a dotted line here. So this is our system here between these 3 points. So they want the total energy of the system, right? Now to calculate the total energy of the system, we have to add all the work done or all the energies acting on all the points. I believe you understand that part. So we must calculate our force. Let's call this work done A, work done B, and work done C. So we must calculate our work done at all these points. So our or find this energy in the system, which is I'll call this. So it's that we need to find work done A, work done B, and work done C. As you continue, you will see there is a pattern that they are more or less the same. So to find our work done A, B, and C, let's go. Let's say to find our value at work done A, right? So I'll draw this again. That is work done A. We have our Q, which was -1. Yeah, -1 nanocoulomb. No, that wasn't -1. So this one was -1. This one was 4. And then we have our work done B. Make it smaller. And then work done C. This one was 3 nanocoulombs. So let's say to find our work done at A, we need to calculate our voltage at A, or we'll use this formula. So our formula will be at half times, because we are going to use this formula here. As you can see, this one. So that's where we get the half, and we have number of Q's. How many Q's we have, right? Yeah. So our work done at A, let's say 4 nanocoulombs. So we'll have our also Q 4 nanocoulombs, because we want to also see on this charge, acting on this charge. Then we have our summation or calculation here. Then we'll have our work done from this point, with this point to A. So from C to A, or from B to A, and from C to A. So therefore our, again it's going to be Q of, I'll call this B, divided by, we'll calculate our voltage 4 pi epsilon naught. And I think so you do remember how we calculate our voltage, right? So this is our Q here, then this part here is our voltage. So voltage on, so this one is voltage for between, you can say, A and B. Then so our distance will be from AR minus RB. Then plus our voltage between A and C. So it's going to be QC over our voltage between A and C, which is 4 pi epsilon naught. Then the distance will be A minus RC. So that will be voltage between A and C. Then that's our voltage for A. Then for voltage for B will be the same. We'll have our half times. Then you can say that is QA. We'll have our QB again. Then our distance from QA to QC. So that will be distance QA, our voltage. Then our 4 pi epsilon will be then the distance between B minus R of A. That's our voltage between B and A plus Q between Q and C. Then it's B and C. I mean epsilon. It's going to be R times or R minus B, and then that will be CR of C. So that will be voltage across BC. So as you can see, there is a pattern as you can see this what we call calculation. So I believe C. How will you figure out C now? So again, C will be the same thing. So we'll have our work done at C. We have our half times our charge at C. Then our formula will be what? It will be now include B and it will include QA. Then we'll have our distance between them. So that will be RC minus RB. Then for A will be 4 times pi epsilon naught will be RA or RC minus RA. So they are the same more or less. And then you just substitute in the values. So you when we come back, then you just substitute in these values, and the answers will then yeah. Then as you can see, this is what they did. This one I believe it's Q1, Q2. So you can just check either, but then it's more or less the same thing. So if you calculate this, in this case Q1 they made this minus -1. So you can say in this case our Q1 is -1 nanocoulomb. Then our Q2 is minus, oh no, it's not minus, 4 nanocoulomb. Then Q3 is 3 nanocoulomb. then the calculations are the same. I will, yeah, that's that's number exercise 9. Then you do your calculation, substitute in the value, then you should get 13 point, you should get 13.37 nanojoules. I hope you do understand this second part of the work done. Now the applications of electrostatic, you can read through it where they are used, ESD discharge or electrostatic discharge, where it is used, uh, how is it used in ICs, your EMP, electromagnetic pulse, lightning protection, or ESD. So yeah, you can read through this. Now we come to magnetism or magnostatic. Magnetos, yeah, magnetostatics. Magnetostatics is more or less similar to electrostatics. The formulas are a bit different, but they are almost the same. So, yeah, you can read through it. Electric field is calculated like this. Then our magnetostatic field or magnetic flux density is calculated with B. And then, as you can see, there is a change. Now, constant from electric field is what do you call epsilon naught. Then our constant for magnetic field is mu naught. Then our H is the electric field or magnetic field strength. Then field application, you can read through this, and here's a formula sheet they give you. You can check through these formulas, but then you are still given a formula sheet, so you don't have to worry about that. Now we come to uh, bio BIOT Sarwat's law. There are two French scientists, so it's a French name. So in this case, we are going to calculate, or in simplest term, you can go read the definition here. What is it used for? And so in the simplest term, we want to calculate our electric field strength or our electric field when a current is flowing through a conductor, which is H. So how do we calculate this? So let's say, as you can see, they give you an example, but let's go here. Let's say you are given a conductor, something like this. Right? You are given a conductor, right? Then there is a current flowing through the conductor. We call that I. Now we want to calculate, let's say at this point here, which we call DH. We want to calculate what is the our magnetic field strength here at this point. So the question becomes how. So that is where our what you call bio or BIOT Sarwat's laws comes in. So our BIOT Sarwat's law says that, let's say you have a conductor. Um, oh, we do have a conductor. What's that? So we have a conductor, right? A long conductor, but then we only take a small piece of that conductor. So we take this piece here, which is really, really small, right? Then we have a length of this conductor, which we'll call dl. So d just means it's a very small length. So L is the length, D is very small, just means it's very small. Then we have our current moving through the conductor, and then we have our P here. That's the point P, or we'll call it, let's say I'll call it also dh, or yeah, p. So now we want to see what is the magnetic field strength, or what is our dh. In this case, very small d, so the h is very small. So what is our dh at this point? And then we'll say this is our r radius. So the formula for this is, so that's the simplest explanation for what is a BIOT's Servet's law. So the formula for this is given that in terms of vector, our dh, it's a vector, that's why we have a line, times our conductor, it's our conductor over 4 pi r, I believe. So it's our conductor over 4 pi r squared times we have our again dl, this value, and dl is also a vector, so we'll get that times x times our r. So r is this, but r is also a unit vector, so it's a perpendicular to our dl, so we take is as a unit vector. So we take our r as a unit vector. And this one is a cross product, so it's a cross product between, I'll call that CP, just remember cross product between our dl vector times our r. So we need to find the magnitude of dh. So the magnitude of dh of a vector is just dh, right? Then our I is just a constant, our 4 pi r squared is also a constant. Now the cross product between these two is what? Our dl and our unit vector. So we need to find first the magnitude of dl, which is dl. The magnitude of a unit vector, just remember it's a unit vector, is also 1. So it's just 1 times sine of the angle between them. So the angle between them is this here, which most of the time call it alpha. So angle between our length of the conductor and the r is alpha. So we get our dh equals I divided by 4 pi l squared times dl times sine alpha. So that's how we get our formula, or that's the basic understanding. So our electric field or strength of the field at this point there. As you can see in the notes, they do show you a process how they get it even there. Then our dh will be, in this case, they didn't remove our, what do you call, dh, so still we have the cross product here. And then our r, in this case, it's not 1. This one was just for 1, but then our unit vector can change in some of the cases. So yeah. And as you can see, our what you call magnetic field strength through different surfaces. Line current, which is this one, which we have calculated here. Then we have our surface, which gets us KDS. This is a new variable. Then we have our 3D object, or yeah, a volume surface, which gets us with JVDV. And then they just show you how do we calculate those values, or yeah. So how do we calculate those values at our point or at different surfaces? That's all they show you. That's our, you can say, BIOT Sarvat's law with different surfaces, line, surface, and then you can also read through this. Then we have a magnetic field strength due to straight conductor, current carrying conductor. So now we have a magnetic field strength, right? Through a straight conductor, so it's perpendicular to our point. So how do we calculate that, or what do they mean by that? So let's say again, let me just go back. Let me just draw it here. We have our line. Just we have our line. We have our line, right? Yes. Sorry, I just need to pause this thing. Yeah, sorry guys. So let's continue. So we have this our straight line here, right? We have our line. Then they say we have our point here H. So this is where we want to calculate our H here. So this is where we want to calculate the magnetic field strength, right? Then we are given our conductor current is moving from this point I. Then we have this line, this short line, which is our length D L, right? Then we have our point A where we want to calculate our strength, and a point B. Then you just draw a straight line from there to there. That will be alpha 2. So so you can say it's a current carrying conductor on it's a strength on a straight conductor due to carrying. So yeah, let's do it again. The field strength is due to the straight current carrying conductor. So that's our field of strength, alpha 1. We call that. Then from the middle of our conductor to there, we have our alpha. And I think so we worked with alpha, and then this is also R. So now in this case, we want to calculate our H in terms of, and then this horizontal line, we call it, what do you call, phi, and then this vertical line here, we call it, or that we call it Z. Just remember that. So that is why they show you it's Z. So that's your, uh, more or less the diagram, understand, right? Then here they just show you how they calculate the values. And I think so from the previous notes, you do remember our DH equals I times, it was what, I times 4 pi R cubed times DL times R, the cross product between R, which is that, as you can see, that we already calculated. Then the new, what do you call, is that our, um, or you can say our value for DL or for R, it's going to be what? As you can see, our if you use Pythagoras already, you can see our R is going to be something like this. So our, that will be, therefore our R squared will be phi square root of phi plus z square root. So that's simple Pythagoras. And then I think so they also show you our r will be the derivative of p. So the derivative of p dp plus our z in terms of derivative of dz. So d just means a small length of z or a very small length of z in terms of z also, which as you can see they give us the value. And then they also show you your dl, they take it as dz. dz z is there then in the direction of az, so that's our unit vector. And then they substitute all these values, then you get your alpha in terms of p and z you get in terms of, but then you substitute all these values into this equation, and then they derive this one. So the important one to remember is this one here, and then even this one, the unit vector calculations. Yeah, and then as you can see, you can also read through for an infinite line or for a semi-infinite line. It's also given, there are two conditions, so we'll do that also. Then let's go to exercise 10. So guys, I will start with yeah, exercise 10. This is where this example I think should help you understand magnetic field strength due to straight current through carrying conductor. And this is where we'll use what you call bio T-Servot's law. So let's start with exercise 10. So as you can see, if we read through it, we have a conductor, positive y-axis, a semi-infinite line with respect to the origin, carrying a filamentary conductor of 2 amps in the direction of minus AY. Then assuming the part of the large circuit. So here they give us two coordinates A and B where we have to calculate our strength or magnetic field strength. So let's start with A. So but before we start, I would recommend you always start with a diagram that makes it easier for everyone to understand the work. So we have our Z plane here, we have our Y plane there, and we have our X plane here. Right? So let's say they say our current is on the y-axis in the negative direction. So let's say our current is on the y-axis. The red line is the current, which is in that direction or in the negative direction of y. So it's going that side. So that's our current flowing, so which we can make our, let's say we can make this 2 amps in the direction AY. And we also call this length. So just remember we call this also A, L, or in the direction of the length. So our we can say that our AL in this case is same as AY, the direction of the current. That's the first thing. So we have our direction correct. Now we go to number A. So A says, let's say we have a point at 2 where our x is 2, y is 3, and our z is 0. So we don't have anything in the z domain or in z, so let's say, I think so we'll put it there. So if you draw a line, that will be 2, and if you draw this straight line down, that will be 3, right? So that's our point there. Then they say we have a semi-infinite line with respect to the origin. So we have our origin. So this is the semi-infinite line. So from the origin, we will have a line to the conductor. Then from the conductor, it's just going infinitely way in in this direction here. Right now to see, so we can put this one here. It will be, we can say this will be 2, this point will be 2 and 3. Think that works for us. Then that will be there. Yeah. Then you see this dotted line here, or we can call this line here. Let me give another color. The orange line here, we call it A phi, or the magnitude of that line will be phi. A phi is just the direction of that. And if you see, A phi is in the direction of AY, because this is our direction of, I mean, AX, sorry. Its A phi is in the direction of AX, if you can see there. So therefore, you can also write our AX direction is same as A phi. Hmm. Now we have this diagram. Now we need to find some angles. As you can see from looking at this diagram, you can say our alpha will be, or our alpha 2. You can say our alpha 2 will be, and just remember, you draw this diagram always respect to the current carrying conductor, or the line where the current is flowing. So your angle alpha will always be with respect to where the current, or on which line it's flowing, the current flow. So in this case, we'll have our alpha 2 here. Mind my drawing, but we'll have our alpha 2 here. I'm just copying this, as you can see. Then your alpha 1 or alpha 1 will be this direction, this one here, this angle here. Alright, and so we'll be using this equation here to calculate our um, direction. Our H. And as you can see, we already have A, L, and A, phi. Alright. So now let's start calculating. So according to this is a semi-infinite line with respect to origin. So we know our alpha 2 will be 0 because of this condition here. So for number A, our alpha 2 is 0, right? Now we need to find the angle for alpha 1. Alpha 1 will not be 90 in this case, because you see there is a angle here. It could be 90 for this case, where it's just straight. As you can see, this is straight. But however, for alpha 1 in this case can be 90, but then in this case alpha won't be 90. So we need to calculate alpha 1. So now to calculate alpha 1, let's do some work here. So you can see that this angle, let me try another color which is different, yeah, green. You see this angle here, this one, yeah. So we need to find the angle in the green to calculate our alpha 1, because we know this is a straight line. If we draw it, it's a straight line. So there are two angles minus that. So our, you can say your alpha 1 will be 180 degrees minus that angle in the green. So now to calculate our angle there, or our alpha 1, we need to see, we need to assume that this angle here is 90, or we can just say that this one is hypotenuse, right? So let me, so we'll have this triangle here, this green triangle. I'm not sure if you can see, but then we'll have this green triangle, which is a right angle triangle. So you can say that's 90 degrees. So we have our value there, which we can say this one is 3, this one is 2, and our hypotenuse is that. Yeah, this is our hypotenuse going in the y direction, it's 3, in the x direction is what do you call y. So you can use any method here now to calculate. So our hypotenuse, this will be, if you remember, this thing will be, you just say 2 squared plus 3 squared, it's 2, just remember that, square root that. So that will give you more or less 13 square root 13. Just mind my drawing, because now I don't have my writing pad with me. So I'm just drawing with the mouse. So then we have our hypotenuse, right? Then you can use either a negative cos theta or sine theta to calculate your angle. So in this case, let's use sine minus 1. Then opposite to sine is 2, so I'll put 2 there, and then 13. That should give you your alpha 1. Alright, so we found our alpha 2, alpha 1. Now we need to find our, let's go back to the equation. So what else do we need to find? So we find this is done, this is done. We have our current, we need to find our phi, right? And to find our phi, you can say, as I told you, that's our phi here, this orange line, or this line here, which is in which, if you check, it's from, we can say from 0 to 2. So from looking at it, we can say the magnitude of phi is 2, right? That's the magnitude of phi. So from looking at it, I believe we have found all these values. So we found our phi, alpha, and 2, or alpha 1 and alpha 2. And then we have our current, which already given is 2 amps. And then using this formula, you will find your value. Then let's say to find our alpha, or our the angle, this it's going to be this times, if you read through it, it says this times AL times A phi, right? And then we already said our AL is minus AY, then the cross product between that and A phi. And I think so, if you look at in your textbook, The cross product between these two will give you, I believe, a z. And if you think about it, it's quite true because let's say this is our y and this is our z. In this case, we are only working with a two-dimensional object where there is no z, right? So when you take a cross product of this, it should give you a z. It's there. I think so. It's part of uh, unit one, I believe. Yeah. So it's part of unit one. You can check it out if you don't remember. And as you can see, they do the same thing here. Sorry for that. So as you can see, they do the same thing here. Alpha 0 and then cos of alpha 1, 0 is just 1. So you can substitute that and that's how they calculate your alpha 1 in this case. You can also have cos negative 1 divided by 3 over square root 13. I think so, yeah. That's your angle and that's your cos of alpha 1 which equals uh, a minus 0.83. You can calculate through it. And in this case, as you can see, they do a two-dimensional drawing, which I think I can recommend. You can do it. It's not a problem. But then they give you a three-dimensional vector. So I believe it's a good idea if you start working in three-dimensional work. That makes it easier for you to understand the work, or just makes it easier to interpret the other three-dimensional work, because now the next example is in three dimensional 3, 12 minus 4. So here we won't use this one. So rather try to use it three-dimensional, or if it doesn't make sense, then just use two-dimensional. I hope, yeah, that should help. Yeah, so let's do what do you call number B. So let me put that there. Number B. So I believe if you understand this example number 10, the rest are more or less the same examples. So I leave these examples for you to practice. And so let's do number B. So again, we start with a diagram. Now in this case, it will be three-dimensional, so the diagram can be a bit confusing. Then again, let's draw our current. Our current is still flowing along the Y. Just remember that. Our current is still flowing around the Y and our direction is still minus AY for the current, which is 2 amps. Just remember that. And at least they do give you the directions which there. That's our current. Now our point should be 312 minus 4. Okay, so we know our x will be 3, y will be 12, then we'll take it down, then our z will be minus 4. So let's see if we can draw this properly. Uh, let's just take it, it's somewhere around here. So make it easier, somewhere around here. Just remember it's a three-dimensional object. So there is dimensions to it. So then we have our goes down 4, then comes something like this. This goes down. Let's see if we can draw it nicely. Yeah, I think that looks better. So our point will be somewhere here. Set down here. So let's use, yeah, yellow. So this is our point there. It's now you, as you can see, we are working in three-dimensional object, and then I'll also extend the current such that it's easier for us to work. What else do we need? Yeah, then I'll just write our coordinates here to help us. It's 3, 12, and minus 4. So that's your coordinates, right? Yeah. Now to let's say now we want to draw the lines for the from here to our current. So again, to find our alpha and every alpha and alpha 1, again you draw whatever wherever the point is, but you draw it to that current. So it will be this line there, then it will be this line here. Then this will be our, you can say, now in this case our we have what do you call three-dimensional. It's not a finite line, so in this case we take it as finite line. So we are not going to have our alpha 1 in that direction. We can still have it, it should work out. In this case, we let's assume our alpha 1 is 180 degrees. So we'll put our alpha 1 here, which is, yeah, alpha 1. Then you can put this one there, alpha 2. So I hope you can see that. So our alpha 1 will be mm, then again that will be our alpha 1. Then to find phi, or let's say, yeah, to find phi or to find our value for phi, it will be always from that point perpendicular to this line here. Most of the time we say, yeah, it's perpendicular to this point here. So if it's perpendicular to this point, so from the center to the a straight line, so these 2 points will be there somewhere there. I hope you can see, so that this line will be our phi, and the value of phi will be, I think so, if you draw a line, it's going big in the what do you call, not, we won't take it, it's x direction, it's more like y. It will be z and x direction. So if it's z and x, so let's say our phi will be what? So it's going in z direction, then x. So as you can see, that's our phi. This is z, then that is x. If you just try to see, or just try to imagine the three-dimensional. So in this case, as you can see, it will be the combination of z value and x value, which will be, x is what, 3, z minus 4. So if we do that, then I think so. Yeah, and I believe you know the distance formula. So the magnitude for phi will be 3 squared plus minus 4 squared, which is 9 plus 16 square root. That should give you 5. That is our phi. Right? Yeah. Now to find the unit vector for phi or this, we need to find the unit vector between what do you call of so we'll have a unit vector of az of our z and our x divided by the magnitude. I think so. I believe you know how we calculate unit vector. That shouldn't be confusing. So our in this case it will be minus 4az, and our 3 will be 3ay or ax, I mean, divided by 5. Our magnitude here, this one is same as that, so which is our phi. Just remember it. So that will be our unit vector for a phi, and I believe you still know, remember our al from a is a y, because the direction has it changed, right? Yeah. Now in this case, let's assume, not assume, let's say our alpha is, in this case, yeah, we assume in this case our alpha 1 is 180 degrees, because it's from the origin to this direction, then it goes, because we have a three-dimensional object, so we are going with this infinite line, not semi-infinite, not this one, but then we are going with this one, infinite infinite line. So if we now we have our alpha 1 oh yeah. Now to calculate alpha 2, I believe you know it's going to be, or even if we check the again, we take the right angle triangle, more or less it's going to be that. So we take our right angle triangle here. Let's do this. Now to calculate alpha 2, we know our this distance here is 12, and we know this distance here is where our it's resting, it's 3. Yeah. So what we can do is either we can find, let's see, this, then this. So we can find this angle here, and then we know our angle. We know our length for y is that, so we only need to find our length for this length here. And I believe it should be, you can calculate it, it should be 13. Uh, let's see, it's going to be, yeah, it's 13. This one here, it's going to be 13 because I believe it's square. 12 square is 144. It's what? 144 plus 9 plus 5 square. 12 square plus, yeah. Let me redraw it. I think so it's confusing. So now we'll find our alpha true, right? Oh no, alpha. Yes, it's alpha 2. So let's draw again. So somewhere down here, we'll take that. Then it goes there. there. That's alpha 1. This is alpha 2. Now let's draw a block such that we know this is a three-dimensional object. And I think so we also need to draw this line here. Yeah. Hmm. So I believe we agree that line is 12. This line here, we agreed it was. So when we calculate our, or when we calculated our, this line, we call this phi, right? Which was 5, I believe. Yeah. So we have our phi and we have our debt. So we can use any method now. So we have this line. So it's this. If you draw it in terms of right angle triangle. So this is what we want, and we have our 5 and we have our 12. And just right, phi is 5. So we can use any method here. You can calculate the hypotenuse, then you find it, or you can use tan minus tan theta. And yeah, in this case, let's use again my sine of alpha 1, which is equal to, then we need to find this hypotenuse, which is 13, because 12 square plus 5 square, square root that gives you 13, which is going to be opposite. So we have 5 there divided by 30. Then you will find your alpha 1. Yeah. Then in this case, I believe we have calculated all these things. And just remember in this question, it's not that you are trying to find h here. You are trying to find all these values, your phi, your alpha 1 and alpha 2, and your direction. They carry more weight. So if you find these four values, then your h is it's going to be correct. So just remember, you're not trying to look for h. They say yeah, you calculate, but then your step-by-step process is first you find phi, you find alpha 1, alpha 2, using these conditions here, or you can read through the conditions, what are the conditions applied to it. So if you can find your alpha 1, no, that's alpha 2, I mean, so this one is alpha 2, just remember that. Yeah. Then to find our also the direction of the whole system, and you just get the dot product. Oh no, not the dot product, the cross product between these two. So your a phi will be minus ay cross 4az plus 3ax over 5. So yeah, you find the cross product between them, and then that should work for you. And I believe that's our done. If you find that, so I believe I showed you the process of how to calculate these values, which are the more important stuff. And if you can calculate these values, then I believe it's just simple substitution in this formula here to find your magnetic field strength. Yeah, so that's exercise 7 for you. Oh, I mean 10. So, and as you can see, they do more or less this. No, that's not it. Yeah. As you can see, they do more or less the same thing as us. They find alpha 2, which is here. So they use this angle. As you can see, this is also, so we can assume this is our hypotenuse. So there is a 90-degree angle there. So they find alpha 1, they said it's just 180. So leave that out. Then as we have the direction, then your phi, as you can see, it's the combination our z and x. Then our direction of phi, it's in this direction. So it's a unit vector. Yeah. And then through the calculation, you get this here. And then from there, it's just substitution, as you can see. Yeah. And same goes for, you have exercise 11, it's the same method. So just check that out. It's the same method, but in this case there are two. So you use the same method for each and every one of them. So you have H1, so you just focus on H1, you leave out H2. So when then you calculate H2, you leave out H1. And then for both of them, as I said, you need to find your phi, your alpha 1, your alpha 2. And if you find these three values, yeah, then you're on the right track. Then you want AL, your direction for the unit vector, and your AX. So if you find these five, yeah. So just remember, it's not that complicated. Just look at it part by part, what you need to find to get to the final answer. So I believe I leave this to you. The other exercise, you go try them out and see how it works. The remaining ones are all more or less the same stuff. Yeah, and I believe we are done with Unit 2. Yeah, we are done with Unit 2. Thank you, guys.